Alright, in this video we're going to use a Laplace transform along with a Heaviside function to solve a differential equation. So here we've got the differential equation y double prime plus 3y prime plus 2y equals g of t. We've got the initial conditions y of 0 equals 0 and y prime of 0 equals 1. And g of t is just going to be a piecewise function. It's going to be equal to 1 if t is between 0 and 1, and it'll be equal to 0 if t is greater than or equal to 1. And we're going to assume here that t is only defined for values of 0 and larger. So really what we're doing here is we're going to use the Laplace transform to solve linear, constant coefficient differential equations with piecewise continuous forcing functions of exponential order. That's really what we're doing if you want a nice, precise bit of terminology. So the first thing I'm going to do, our function here, g of t, this is going to be a long problem, so because I'm really going to try to go through a lot of the steps. So a couple things. We're going to use a lot of Laplace transforms, so I would certainly have a table of Laplace transforms handy. I'm going to jot some of them down, but again, I will be referring to those. So here's our function g of t. Okay, it's 1 if it's between 0 and 1, and then it's 0 everywhere else. So the first thing I'm going to do is I'm going to write that using one of our Heaviside functions. So I've got videos on those. You might want to check those out. But notice our function here. It's basically turned on between 0 and 1. And the way that we can write that in terms of a Heaviside function is that would be h of t minus h of t minus 1. And recall, this is basically a function that turns on at t equals 0 and turns off at t equals 1, which is what this one is doing. So again, if you haven't seen Heaviside functions, I've got some videos on those. You might want to check those out. But you could also write this one equivalently as 1 minus h of t minus 1. But I think I'm just going to use this form on the left because that's what I've talked about in some other videos. Okay, so we've got the function we're trying to solve here. I'm just going to rewrite it. We've got this function y double prime plus 3y prime plus 2y. That equals our function g of t. But g of t, again, we can now write using our Heaviside functions. So h of t minus h of t minus 1. And what I'm going to do now is I'm just going to take the Laplace transform of both sides. So I'm going to take the Laplace transform of the left side and of the right. And recall, since it's linear, you can basically just bust it up. So I'm going to take the Laplace transform of y double prime. I would take the Laplace transform of the term 3y prime. You can just pull the 3 out front. So I'm taking the Laplace transform of y prime plus 2 multiplied by the Laplace transform of y, little y. And then I'm going to take the Laplace transform of the right side as well. So the Laplace transform of this Heaviside function, h of t, minus the Laplace transform of h of t minus 1. So you can't see it here off to the side. I've got a big table of Laplace transforms here. Let me show you just so you know that I'm not joking here. So I've got a big table of Laplace transforms that I'm going to be using. And again, I've never taught differential equations. It's been a while since I've been a student. I don't know how many of these you would be honestly expected to have memorized. You know, if you're taking a quiz or a test over this stuff, certainly ask. So if it was me, you know, being a student working on this stuff, I would definitely have, you know, some of this stuff. I would have a table right there in front of me, I guess is what I'm trying to say. So, okay, so let me go back to my example where I wanted to be. Where'd you go? Okay, so we're taking the Laplace transform here of all this stuff. And recall, you know, again, you can check the Laplace transform of y double prime. That's given by the formula. That's going to be little s squared. We use capital Y of s minus s times capital Y of, little y of 0. See, I'm already, got to be careful here with our capital Y's and our little y's. So it's s squared capital Y of s minus s times little y of 0. So this is where our initial conditions are going to come into it. Minus y prime of 0. So I'm just using the formula for the Laplace transform of y double prime. That's this part. And then we'll just keep going. So then we have plus 3 times the Laplace transform of y prime. The Laplace transform of y prime, that's given by the formula s capital Y of s minus y of 0. And I'm going to run out of room here. Plus 2 times the Laplace transform of y, and that's given by capital Y of s. Now, we have to take the Laplace transform of h of t minus the Laplace transform of h of t minus 1. So I'm just going to write that down because I'm going to compute that here off to the side. So we took the Laplace transform of the left side, and we still have to do it on the right side, but let me show you how to compute that part really fast. So one of the formulas, let's see, here we go. So one of the formulas for Laplace transforms and Heaviside functions, because that's what we're doing here. So let's see, the Laplace transform, the formula that we're going to use here, we've got the Laplace transform of some function f of t minus c multiplied by h of t minus c. The Laplace transform of that is e raised to the negative c multiplied by s. And then we take the Laplace transform of whatever our function is, little f, and that gives us capital F of s. Okay, so in this case, we've got to compute 2 Laplace transforms. We have to compute the Laplace transform of h of t. And the way that I could write that is, well, the function that's being multiplied out front, that's just, you could think about that as being the constant function 1. And then I could write h of t as just, well, h of t minus 0. And according to our formula, we'll get e raised to the negative, well, 0 times s, or e to the 0 power. And then we have to compute the Laplace transform of 1. And e to the 0, that's just 1. The Laplace transform of 1, that turns out to be 1 over s. So the Laplace transform of the Heaviside function h of t, that's just going to be the function 1 over s. And if we do the same thing for our other function, we would have the Laplace transform. Again, you could think about the function in front of h of t minus 1 just as being 1. So then we would have h of t minus 1. So in this case, it says we'll get e raised to the negative power of c multiplied by s. C in this case is just going to be equal to 1. So we'll have negative 1 multiplied by s. And again, the Laplace transform of 1, that's just 1 over s. So we'll have e raised to the negative s divided by s. All right, so I'm now going to go back. I said this one's going to be pretty long. I'm going to go back and I'm going to start simplifying the left side of my equation. And then I'm also going to just plug in what we just found here into the right side. So the Laplace transform of h of t minus the Laplace transform of h of t minus 1. Okay, so let's go back and use our initial conditions. So we've got s squared capital Y of s minus, let's see, so we said that y of 0, and so y of 0 was equal to 0, and y prime of 0 is equal to 1. So I'm going to substitute those in. So we would have minus s times y of 0, which we said is 0, minus y prime of 0, which is 1, plus 3 multiplied by s multiplied by capital Y of s. Again, we said y of 0, that was just equal to 0, so I'm not going to write that down. Plus 2 times capital Y of s. And then on the right side, again, after taking those Laplace transforms, we said that the Laplace transform of h of t, that was just going to be equal to 1 over s. And the Laplace transform of h of t minus 1, that's e to the negative s divided by s. So let's just keep simplifying here. So s multiplied by 0, you're gone. What I'm trying to do now is just to solve for this term, capital Y of s. So we can do that. Let's get rid of this stuff. Okay, so we have s squared times y of s. Let's see. So we've got this minus 1. That doesn't involve y of s. So just a little bit of algebra. I'm going to add that to the right side. So we have 1 over s minus e to the negative s over s plus 1. Let's see, we would have plus 3 s multiplied by capital Y of s plus 2 multiplied by capital Y of s. And again, now I'm just going to solve for y of s, so I can factor the y of s out. I would have y of s equals, let's see, we could, So we could factor that out. We would have y of s. Left over, we would have s squared plus 3s plus 2. Again, equals all this stuff on the right side. Now I'm going to start rewriting this a little bit. So I'm going to get common denominators. We could write, plus 1 as plus s over s. Notice they've all got a denominator of s. I'm going to break this up. I'm going to write this as s plus 1 over s, and then I'm going to have my other term e to the negative s over s. And the reason is it's going to this corresponds. It's going to correspond to a form. If you again look at your table of Laplace transforms, these are going to fit one of those forms. That's why I'm doing that. So again, it's really just kind of looking at those tables and trying to make everything sync up. Okay, so now we've got capital Y of s. I can just divide both sides now by this s squared plus 3s plus 2. So I would have s plus 1 divided by s. That would all get divided by s squared plus 3s plus 2 minus e to the negative s divided by s. And again, we would have s squared plus 3s plus 2. So we're just really kind of getting going here. So again, like I said, this is going to be kind of a long problem. And again, let's take summary real quick. What have we done? All I've done was just wrote my function g of t using Heaviside functions. And then all I've done is just taken Laplace transforms of both sides using the table of Laplace transforms. That's everything I'm doing here. And then it's just, again, just doing some algebra to isolate this term capital Y of s. That's what we've done so far to get to this point. Okay. So now what we're going to do is we're going to take the inverse Laplace transform of both sides. That's what we're going to do at this point. So let me make sure that I haven't done anything too crazy here. I don't think so. So we want to take the inverse Laplace transform of both sides. So again, we can do this in pieces because this Laplace transform is linear. And again, all they mean by linear is you can just break it up. Okay, so I'm just writing, hey, we're taking the inverse Laplace transform of both sides. Okay, so now I'm just going to simplify these a piece at a time. That's all I'm going to do. So I'm going to work on this inverse Laplace of s plus 1 over s multiplied by s squared plus 3s plus 2. And at this point on the left side, when we take the inverse Laplace transform of capital Y of s, this is just going to give us our function y of t. So at this point, all we have to do is just figure out this inverse Laplace transform, figure out this inverse Laplace transform, put them together, and we'll have our solution. Okay, so let's start off by finding this inverse Laplace transform of s plus 1 divided by s multiplied by s squared plus 3s plus 2. So what you would have to normally do in this case is to bust it up, you would break it up and you would want to use, to use your table of Laplace transforms is, you basically do partial fractions on this. So it's just going to be a lot of simplifying using partial fractions at this point. So using partial fractions. And the first one's kind of nice because if you factor the bottom, if you factor s squared plus 3s plus 2, that factors as s plus 1 multiplied by s plus 2. So, okay, this one's set up to work a little bit nicely. Okay, so we can cancel out the s plus 1 and the s plus 1. So we're left trying to find the inverse Laplace transform of, we've got 1 over s multiplied by s plus 2. So now this is where we're going to do partial fractions. To basically put this in a good form so that we can use our table. Okay, so again, kind of off to the side here. Okay, so recall with partial fractions, these are both linear terms in the denominator. We could write 1 over s multiplied by s plus 2. We can write that as a over s plus b over s plus 2. And our goal is now to figure out these constants a and b. So again, if you've forgotten partial fractions, got tons of videos on these. This is normally something, again, you see in Calculus 2 when you're learning all your different integration techniques. So if you're watching this, that means you're in differential equations. So I'm probably going to go through this a little bit faster. We're multiplying both sides now by s multiplied by s plus 2. I'll do the first one. So s multiplied by s plus 2. On the left side, we'll just be left with 1. On the right side, when we distribute, we would have a multiplied by s plus 2 plus b multiplied. Well, there the s plus 2's would cancel, and we would just be left with s. Again, we're trying to figure out a and b. Notice if you let, let's see, s equals 0. If we let s equal 0, we would have 1 on the left side. We would have a multiplied by 2, or 2a. Notice the term involving b times s would be gone. So if we solve, we'll get 1/2 will be the value of a. Likewise, notice we could let s equal -2. And if you let s equal -2, well, you still got 1 on the left side. This first term involving a is now gone. You have -2 multiplied by b. So -1/2 will be equal to b. Okay, so I'm trying to again find this inverse Laplace transform of 1 over s multiplied by s plus 2. But instead what I'm going to do is find the inverse Laplace transform. We said 1 over s times s plus 2. We said we could write that as a over s. Well, a is equal to 1/2. We said b was equal to -1/2. And again, now we can just use our table of values. So hopefully you can see mine well enough. Let's check here. So forget about the constants for a second. Forget about the 1/2 on top and the -1/2. Really, you can factor those out. Just worry about the 1 over s and the 1 over s plus 2. It says if you have 1 over s, can you read that? Probably not. If you got 1 over s, it's the very first one. The inverse Laplace transform of that is 1. If it's 1 over s minus a, it's e to the at. So we've got 1/2 multiplied by the inverse Laplace transform of 1 over s minus 1/2, and then we would have the inverse Laplace transform of 1 over s plus 2. So now I'm just getting this stuff again straight from a table. Just straight from a table. So the inverse Laplace transform of 1 over s, that's just 1. The inverse Laplace transform of 1 over s plus 2, that's going to be e raised to the, okay, so normally it's in the form s minus something. So you could write this as s minus -2. So we get e raised to the -2 multiplied by t. Okay, so 1/2 minus 1/2 e to the -2t. Okay, so what have we done at this point? What we've done is we found the the inverse Laplace transform of the term s plus 1 divided by s multiplied by s squared plus 3s plus 2. So this part is going to be useful. That's going to be part of our solution. And now I'm going to go back and I'm going to do the same thing. I'm just going to figure out the inverse Laplace transform of the other term. So now we're going to figure out the inverse Laplace transform of this other term. So now let's find the inverse Laplace of e to the negative s divided by s times s squared plus 3s plus 2. Okay, this one's going to take a little bit more work. And the thing to notice in this case is that this is of the form. So this is of the form. We're trying to find an inverse Laplace transform. We've got e. We could write this as e to the negative cs multiplied by some function f of s. So in this case, we're trying to find, what are we trying to find? We've got our c value is negative 1. Our function f of s is going to be this 1 over s multiplied by s squared plus 3s plus 2. Okay, now there's a formula for these in this case. So the formula that we're going to use in this case, it says if you've got an inverse Laplace transform of a function of the form e to the negative, where do I have it here? E to the negative s times f of s. Again, I'm just using a table here. That gives us a function of the form f of t minus 1 times h of t minus 1. And again, that's because of my value up here of negative 1. Okay, so again, this is all just table stuff. So the next thing we have to do is now we need to find the inverse Laplace transform of 1 over s multiplied by s squared plus 3s plus 2. Well, I again can write s squared plus 3s plus 2 as s plus 2 multiplied by s plus 1. And again, I'm going to do the same thing. I'm going to do partial fractions. So partial fractions, so we've got 1 over s multiplied by s plus 2 multiplied by s plus 1. Again, these are all linear. I can write this as a over s plus b over s plus 2 plus c over s plus 1. If I multiply both sides by the denominator, s times s plus 2 times s plus 1, I'll be left with 1 equals a multiplied, okay, the s's would cancel. We would have s plus 2 times s plus 1 plus b multiplied by s times s plus 1 plus c multiplied by s times s plus 2. Now, I'm not going to go through, again, you could let s equal 0, we could let s equal negative 1, and then you could also let s equal negative 2 to solve for a, b, and c. And when I did that, I got a to be equal to 1/2, I got c to be equal to negative 1, and I found b to be equal to 1/2. So again, that's kind of skipping those steps, but you still have to work a little bit to find those. So at this point, okay, let's, where are we at here? So if we now take the inverse Laplace transform of a over s, so that's going to be 1/2 over s, plus b, that's 1/2 over s plus 2, plus c, so that's plus negative 1 over s plus 1. And again, this inverse Laplace transform of all this function, that's going to be my capital F of S. Okay, so I need that function. That's my capital F of S here. Okay, so if I compute that, let's see, what have we got here? So we said the 1/2 comes along. The inverse Laplace transform of S, that's just 1. Okay, plus 1/2. The inverse Laplace transform of S plus 2, again, that's going to be e to the negative 2t. And then we've got our minus 1. The inverse Laplace transform of S plus 1, that's going to be e to the negative t. Okay, so we're almost there now. Almost there now. What's the one part that we need? So if we compute this inverse Laplace transform now, where'd it go? This inverse Laplace transform of e to the negative s multiplied by 1 over s times s plus 2 times s plus 1. Okay, so we've got our function here. So it's going to get multiplied by h of t minus 1. In this case, our function here that we just found, where'd you go? This is going to be our function little f of t. So we said that this is going to be equal to f of t minus 1 times h of t minus 1, again just using our table. So we figured out that f of t was equal to this function. So now just replace all the t's with t minus 1. So in that case, if we replace all the t's with t minus 1, we would have 1/2 plus 1/2 times e to the negative 2 times t minus 1 minus 1 e to the negative, e to the negative, let's put our parentheses in there, t minus 1. And again, that's getting multiplied by h of t minus 1. Woo, okay, long stuff here. Again, just using our formula here. And the last thing we need to do now is just put all of this stuff together. So where did everything go? Okay, so in summary, so the inverse Laplace transform of y of s, the inverse Laplace transform of y of s, that's just going to be our function y of t. And we said the inverse Laplace transform of this function s plus 1 divided by s multiplied by s squared plus 3s plus 2. We computed all of that. I think I've lost the piece of paper that it was on. Where'd it go? So when we computed the Laplace transform of this term, when we computed that, we got, what did we get? We had 1/2 minus 1/2 e to the negative 2t. And then it says we have to subtract away the inverse Laplace transform of this e to the negative s divided by s multiplied by s squared plus 3s plus 2. That's what we just figured out. That's all of this stuff. So let's see, that's going to be 1/2 plus 1/2 e to the negative 2t minus 1 minus 1 e to the negative t minus 1 power, all being multiplied by h of t minus 1. So I've now put everything together. Do I have all my parentheses in the right place? I think so. And that, to me, now looks like that is going to be our solution. Trying to make sure I didn't leave anything out here. All looks good to me. So, whew, again, long problems. So what did we do? We used Heaviside functions. We took a lot of Laplace transforms just using formulas. You know, we plugged in our initial conditions, our y of zeros and our y primes. And then it was just using partial fractions to put, again, things in a good form to match up with our table. We had to use this function involving Heaviside functions, but other than that, I don't think there's anything else that that we left out. So again, it's just a lot of putting things in the correct form so that you can use your tables. So I'm sure there will be questions. Feel free to please post and ask. If I can't help you, hopefully somebody else can put you in the right direction. If you would like to see another one of these, by all means, let me know and I can make some more. And yeah, we'll go from there. So, all right, friends. Again, not an easy procedure. I mean, in a sense, it's just really long, and it's just using tables. So, again, I would have that table of Laplace transforms open right in front of me as I went through these. So, all right, again, I hope this helps, and good luck.